Alright, so in this video we go over section 3.4, local extrema, and the first derivative test. So in this section we will define what increasing and decreasing functions are, and we will describe those intervals in which a function is increasing or decreasing, and then we will use the first derivative test to find whether a function has a minimum or a maximum at a critical point that we will also find and define. So first of all, let's say let's define what increasing and decreasing functions. So we are going to consider a function f of x, or just f, defined on the interval a to b. So there's two cases here. Number one, for both cases where x1 is less than x2, so we assume, just in general, that the first number is smaller than the largest, and then this is smaller than the next one rather. And well, if the function evaluated at x1 is less than the function evaluated at x2, well, then we will have an increasing function. But otherwise, if the function evaluated at x1 is greater than the function evaluated at x2, we will have otherwise a decreasing function. So to illustrate this, let's briefly look at this couple of graphs. So what do we have here? Well, some function with x1 and x2. If we do the graph of a decreasing graph, and we do the same with the graph of an increasing graph, x1 and x2. So in this case, well, so we will define this y value where f of x1 and f of x2. Same here, f of x1 and f of x2. Notice in this case, the f of x1 is larger than f of x2. Let's write it in terms of an inequality. And over here, f of x1, it's a value that is less than f of x2. And well, because yes, this value is larger in the y direction than this first value. So this confirms what we have in the definition. What do we have? Well, we have an increasing function, or rather a decreasing function, and increasing. Okay, so that confirms what we have here in this definition box. All right, but of course, I mean, these kind of graphs won't have only one behavior. Well, there are cases in which we may have a function that is only decreasing or only increasing. We may have other graphs, I don't know, maybe something like this, that, you know, we may have something like that, for which, well, we have a function where increases, and increases. And there are intervals where the function decreases, and also decreases and decreases. So depending on the given function, we may observe its behavior more than once, at more than one of the given intervals. So let's look at an example, a very brief example involving a graph. And well, we have this graph of f of x. It's not defined in explicit form, but they're giving us some points A, B, C, D, and E. Well, to make our lives easier here, let's put numbers. I'm going to put -3, -1, 1, 2, and 3. So they're asking us for the interval on which f is increasing and where f is decreasing. Well, we need to look at the graph and observe the intervals in which the graph is going up. All right. So in particular, well, um, let's see. Let's identify the intervals where it's going up, and I think over here it's also going up. All right. So let's make a list of these intervals. So, okay. So f of x is increasing on the following intervals. Well, we need to list the interval -3 to -1. And well, okay, let me list the following interval where it's increasing. That is from 1 to 2. And then finally from 3 to, well, notice this arrow pointing over here in this direction implies that the graph goes on forever. So from here we can say that it also increases from 3 to infinity. All right. And well, the formal way, the more formal way to describe this is by putting the union sign, the union symbol, to connect these two sets. However, when you do this on the homework, the most likely the homework will ask you to list these intervals as separated by commas. So either way is fine. All right. So now we will describe the intervals for which f of x is decreasing. Well, so let's look at the intervals where the graph is decreasing or going down, right? So the first interval, well, is described by the point -1 to 1. All right, so that's -1 to 1, comma, instead of the unit symbol, the other will be from 2 to 3. All right, so that's one example for which we are given the graph, and we need to determine whether this is increasing and decreasing. Okay, so there's another case that we will later do in the algebraic version of this problem, in which, well, it's either always increasing or always increasing or always decreasing. How do we know that graph? Well, you'll see how do we do that one. All right, so here we have a theorem in which we suppose a function f of x is differentiable on the interval a, b. Oh, by the way, I need to go back a little bit to the graph. Notice in this case, I had this -3 with parentheses. All right, notice I had it with parentheses, even though we have a solid point on the end point here. So you may think, well, it should be increasing on the closed interval. You might argue that it should be bracket instead. Well, here is a problem. The problem is that the at any point on the graph, there is only one point of tangency, like this point, that point. There's only one point, you know, except for the point where we have the cusp, like this point, and points where we have endpoints with a solid dot. Over here, at the point where there is a cusp, there's infinitely many possibilities for tangent. Well, we may have this tangent, we may have this other tangent, fully horizontal, etc. Many different tangents. And over here, well, at this point, we may have this tangent, that tangent, that tangent, many different possibilities, and in some cases the slope of those tangents are positive or negative. So because in this case we are describing f of x to be increasing, then well, we need to consider only the part for which it's increasing. So, and that part is by excluding the endpoint, that is by just using um, by just using an open interval. That's how we describe, but otherwise we would be in trouble if we use the closed interval. Okay, so what are we going to have? So we are going to take the derivative of whatever given function, and if the derivative is positive, that is, recall that the derivative represents the slope. The slope of what? Well, the slope of the tangent line at a given point. And if all the slopes, well, we're not going to calculate all the slopes at a given interval. That's not a feasible task. But all we'll do is look for the sign of the slope, which is the sign of the derivative. Well, then we're going to have an increasing function. Again, let's go with the graphs over here. So in an increasing graph, see how the slope is positive. The slope of the tangent, it's positive all the time, as opposed to the slopes for the decreasing graph, which in this case they are negative. Okay, so that's the counterpart of this definition. Well, if f of x is negative, so that is, well, how about we highlight that? F of x is positive, then f is increasing. But otherwise, f prime is negative, that is the derivative is negative, well, then f is decreasing. Okay, so in this case, the values of x for which the function is increasing or decreasing will always be represented as open intervals for the issue that we just mentioned before, not the closed interval, only the open intervals. All right, and so for the first derivative test, so to determine the local extrema of a non-constant function that is continuous, it has to be continuous on the interval, on the open interval that we want to do this process. Typically, we're going to use the entire negative infinity to positive infinity function, unless otherwise stated. So number one, the first step to go about this process is to find the critical values. All right, and we get the critical values by taking the derivative of the function and set it equal to 0, and find the functions for the values rather for which the derivative is either 0 or it's undefined. So that's part A. Take the derivative and find the critical numbers. Part B is to draw an analysis line, and well, I do additional work to be more visual with everything that we do about this. That is, I do a table that, well, I'll show you how it works in a minute. So, and we do this to test the critical values to determine the end behavior of the derivative. Again, the end behavior right here is to tell us whether the function increases or decreases. And well, when a graph changes from increasing to decreasing, then we have a local maximum, and otherwise when it changes from decreasing to increasing, then we have a minimum. Going back to the graphs right here, notice in this case how the graph goes from increasing, that is, these positive signs represent the signs of the slopes of these tangent lines. It goes from increasing to decreasing, negative slopes, but what do we have? We have a maximum. Otherwise, in this case, if we go from negative slope to positive slope, well, what do we have? It's a minimum. It's a minimum value. All right, and again, there's another maximum, there's another minimum here, there's another maximum. Yes, at this cusp, the derivative is not defined, but still we have a local maximum. So minimum, maximum. All right. Let's go ahead and look at an algebraic example for which we do all this process. The third case, when there is no sign change, well, so what we do, our conclusion is that there is no local extremum, or that is no maximum, no minimum. So let's look at the function f of x equals to, what do we have? X cubed minus 12x plus 1. Okay, letter A. So I'm going to show all these examples in a step-by-step fashion, just so you can see what's the first step, what's the second step, etc. So we need to find all the critical values, that is, the values of x that correspond to horizontal tangent lines and potentially vertical lines. I forgot to write this down because we'll look for both. So these values will occur when the derivative is 0. That is, okay, let's highlight this part. These values occur when the derivative is 0. So let's take the derivative of the function. So f prime of x, which is 3x squared minus 12. And well, what do we need to do? We need to set this derivative, set it equal to 0, and solve for x, solve for the variable to find those critical values. That is, okay, first of all, we will solve this polynomial, this derivative, which is a polynomial, by factoring the GCF. So what I'm going to do here is, notice in this case, I can divide both sides by 3. So let's do the division by 3. Or factoring the GCF and then divide, but well, let's just divide both sides by 3 to get x squared minus 4 rather equals to 0, and then we can factor this as a difference of squares. So x plus 4 times x minus 4, and that equals to 0. And well, so over here x equals to negative 4 and x equals to 4. So these two are the critical values. Let's highlight these critical values, x equals to negative 4 and x equals to 4. Okay, so for part B, we are going to use the value that we got in part A to find open intervals on which the function is increasing and decreasing. And then the open intervals, okay, increasing and decreasing. So what are we going to do? I'm going to draw a number line. And well, we are going to slice and dice this number line where the critical numbers are, that is negative 4 and positive 4. All right, so this is what's going to happen when I slice and dice this number line. This will generate me 1, 2, and 3 sub intervals to test. Okay, and let's first of all describe this for these 3 intervals. Number 1, okay, I'm gonna highlight. You don't need to highlight this. Okay, so this first interval, if we describe it using interval notation, I'm gonna go to the box below here. I'm gonna call that negative infinity to negative 4, and it's an open interval, so that's where this first interval goes through. The second interval is going to go from negative 4 to 4. And the third interval is going to go from 4 all the way to infinity. So let's write that down. From 4 to positive infinity. Okay, well, so what are we going to do? We are going to take a test value to determine the sign of f prime, and this way, from there, we will conclude whether the function will be increasing or decreasing. So pick a test value and then evaluate the sign of f prime. Okay, so let's see. So we are going to pick our favorite number in between each interval. So pick your favorite interval, the favorite value, for example, anything within the first test interval that is a number less than negative 4. I'm going to choose negative 5. And then I'm going to choose between negative 4 and 4. By the way, try to choose the easiest number possible. Here I'm going to choose 0. However, you cannot choose critical numbers themselves or numbers that are restricted values from the original function. Well, in this case, there are no restricted values to the function, so this will be fine. And then any value in this interval that is from 4 to infinity, I will just use the number 5. So our test values, let's list them here, -5, 0, and 5. And well, so let's say test x equals to -5. We are going to test on the derivative. Let's recall that the derivative is 3x squared minus 12. Okay, let me write it down again. F prime of x equals 3x squared minus 12. We're going to use this function to evaluate at the derivative, evaluate the test values. So evaluating at -5, we're going to get the following. So -5 squared is going to be 25. 3 times 25 minus 12. Well, in this case, this will be 75 minus 12, which is 63. But ultimately, we really don't care about the value. What we care is that this is a positive number. In other words, 63 is greater than 0. That means positive. All right, so we're going to mark this on the table as a plus with a positive. And on the number line, a positive derivative, the fact that the derivative is positive, it means that the derivative, the function is increasing on this interval. Okay, let's do the second test value. Test x equals to 0. So f prime of 0 equals 3 times 0 squared minus 12, where, well, let's plug in 0 and 0. That equals to 0 squared, which is 0, times 3, that's a 0 minus 12, that equals to -12. In this case, well, we have a negative number, well, that is less than 0, negative. And well, let's mark that on the table. The sign is negative. That means that the original function is decreasing on this interval. Okay, let's see what do we get for the next test value. All right, so test x equals to 5, and f prime evaluated at 5 equals to 3 times 5 minus 12. And okay, let's write this 5 down, plug it in, and same quantity essentially, 5 squared, which is 25 times 3, that's 75, minus 12 equals to 63, which again it's also a positive number, which implies, well, let's put that positive here. That means because the sign of the derivative is positive, is the function is again increasing. So our conclusion is that the function is increasing decreasing and increasing again. Okay, so let's go back to this picture that we did before. So I'm just going to use a dashed circle here, or dashed kind of curve right here to show the behavior. Well, notice, because now we're going to use this information to determine whether we have a maximum or a minimum or maybe nothing. Well, so in this case, since we go from increasing to decreasing, we are essentially reaching a maximum point. Over here, that happened around -4. However, around 4, we're going to have the opposite behavior. We're going from decreasing to increasing. So this point right here will be a relative minimum. Now, we are going to find that relative maximum and relative minimum respectively, not anymore on the derivative. The derivative of the function was only used to find the end behavior, to find the sign of the slope, to help us determine whether it's increasing or decreasing and at which intervals. And then from there, now that we have the information that we have the relative maximum and minimum, well, so we have a relative maximum at 4. Okay, let's call this a 4. I mean a max at -4 and a min at +4. Okay, so maximum. So evaluate not the derivative, but actually the original function f of 5. So the original function in this case, okay, let's write it down again. That's the original function was supposed to be f of x equals x cubed minus 12x plus 1. All right, so here, yeah, you might want to use a calculator. We're going to do some calculations here. So let me see what I get with some of the calculations here. So we need to cube the 5, and then minus 12 times the 5 plus 1. Well, so let's see what do we get. So well, actually, you know what? I think I did let me take this back, because I think I did a little mistake on the factoring, and so with the critical numbers. So let me take this back. So plus 2 minus 2, that was supposed to be the difference of squares. So you may have noticed that when at the beginning of the problem. Okay, let me take this 2. -2 and x equals to 2. Apologies for that, but well, at least I realized on time. And well, nevertheless, that's not going to change over here, because you will see what's going to happen here. So this is still going to be a -2 and then +2. And well, the test values are still within the intervals of testing, so that's still gonna be fine. So let me erase all of this. So that should be to -2, -2 to 2, and 2 to infinity. Well, it still works anyway. Okay, so in this case, we need to we're gonna have a rel max at -2. That's a -2 cubed minus 12 times -2. That's going to give us, using a calculator, that's a -8. And 12 times 2, that's 24. Negative times a negative is positive, and plus 1. So 24 minus 8, that's a 16. 16 plus 1 equals 17. So we need to actually write these relative maximums as order pairs. All right, that means we need to write the x value, -2 and 17. So that is our rel max. We can abbreviate this as rel min, rel max. That means relative minimum, relative maximum, respectively. So we're going to do the same for the other critical values, that the one for which we found out that it was a relative minimum. So f, the original function, f evaluated at +2, That's a 2 cubed minus 12 times 2 plus 1 equals 2. Okay, let's plug in the value of 2. 2 and 2. That's going to give us 2 cubed, which is 8, minus 12 times 2, which is 24, plus 1. And well, in this case, 8 minus 24 is negative 16. Negative 16 plus 1, that's going to give us a positive, that is, well, that's supposed to be negative 8, and negative 15. All right. So this means in order pair, the point 2 comma negative 15. Okay, so that's where the relative mean is located at. So relative mean. All right. So a very typical part of this question is to use all this information to sketch the graph of a function without even using a graphing calculator. Well, in this case, I provided the graph of this function. Well, this one came from the textbook, for which, well, the graph of this function pretty much represents everything that we did analytically. You know, we found out that this is the interval where the function increases. This is another interval where the function increases, and this is the interval where the function decreases. And here are also the maximum, the relative maximum, and the relative minimum that we also got algebraically, you know, and everything pretty much checks with all the definitions of what increasing and decreasing is, and all about maximums and minimums. So this is the first example. Of course, there's a little bit more about this that is called the second derivative test, which tells us about the concavity of the function and if we have points of inflection. However, that's going to be left for a section that is in a further chapter. In the meantime, we're going to do only the first derivative test. Let's go ahead and do another example. So for the function f of x equals x cubed plus 1, let's do the same. Find the critical values that correspond to horizontal or tangent or vertical tangent lines. And well, again, these come from setting the derivative equal to 0. So f prime of x, 3x squared, and then from here, set the derivative 3x squared equals to 0, divide both sides by 3 to get x squared equals to 0. And well, x equals plus or minus the square root of 0, but well, plus minus the square root of 0 is simply 0. So that's the only critical value for this given function this time. Only one critical value. So let's see, how do we go about that situation? Well, we do the same. Use the values from part A to find the open intervals on which the function is increasing or decreasing. Well, so in this case, let's do the number line again. Let's do this number line. And well, in this case, we will only have one single critical value. That is the only critical value is x equals to 0. That means that we will have 1 and 2 intervals to test. And we are going to test the values for each interval. Okay, so in this case, I will choose the easiest values possible. In this case, I'm going to use -1 and 1 as test values. However, we still need to describe the intervals that we use to test. In this case, this interval right here will be the interval comprised from -infinity to -1. And this interval right here will comprise by the interval, or will be described by the interval, well, actually 0. 0 to infinity, negative infinity to 0, and 0 to infinity. Okay, so the sign of f prime. So what do we do? So we need to test these values on the derivative of the function. So we will test x equals to -1, and we will test x equals to 1, where in the derivative. Testing those values in the derivative will tell us the sign of the derivative to later conclude that the function increases or decreases. So f prime evaluated at -1, that'll be 3 times -1 squared, and same over here, f prime 3 times 1 squared. So let's plug in the actual values, the critical values, and see what we get. So -1 squared is 1 times 3, that equals to 3, which in this case is a positive number. And let's mark that here in the table. Okay. For the second calculation, we have also 1 squared, which is 1 times 3, which is 3, which also happens to be greater than 0 or positive. Well, what is going to happen in this situation? So when we go back to our number line right here, we will find out that this is increasing because the sign of the derivative is positive, and this is also increasing. So increasing, increasing also. And well, so in this case, there's no change between increasing to decreasing or decreasing to increasing. For this reason, no relative extrema. In fact, we have a function that is always increasing. It's not going up and then going down, nor going down and going up. It's always going up. So when it comes to relative maximum, none of them. All right. However, we may still be asked the intervals for which the function is increasing. So f of x, when we put this together, we need to list them as either in commas or with union symbol. However, it looks like our textbook uses the commas instead of the union sign. So in f of x increasing on the interval -infinity to 0, comma 0 to infinity. I know you might argue about, well, if we look at the graph, this graph is always going up. It's always increasing. Yes, that is true. It's always going up. However, precisely at the point where we have this horizontal tangent, exactly at that point, the graph is flat. It's neither increasing nor increasing. That's the reason for which we need to write this in separate commas, making sure that we exclude that critical value, because at that critical value, it's neither increasing nor decreasing. On the previous example, we should have done the same as well. So let me go back. Increasing on the following intervals, it's increasing on -infinity to -2, comma, to infinity, and then f of x decreases or decreasing on the intervals, on the other interval actually, that is on -2 due to. So the The point here is that we may need to list these intervals as commas, separated by commas. All right, and well, that was also our second example. And again, everything checks out here. So that's the graph of y equals x cubed plus 1, which is the cubic function shifted 1 unit up. The other order pairs, well, don't worry, one of them is an x-intercept. And well, here what we wanted to see is, or rather to focus, is the point of tangency for this function. Okay, let's keep going with more examples. So now we're going to look at the function f of x equals 1 over x. So what about this one? Well, as opposed to the previous example, so we have a function that now has restricted domain. For example, look at the denominator. So here we have 1 over x and the denominator cannot be 0. So x cannot be 0. That means we cannot use this as one of the test values, and we won't find a function, a max or a minimum at this value. You'll see what's going to happen with this particular case. So, so let's see. Let's take the derivative. So this is the same. So f of x is the same as x to the negative 1, where f prime equals negative x to the negative 2, which reduces to f of x equals to negative 1 over x over 2. I mean, negative 1 over x squared. All right, so what we need to do is to set the denominator, or set rather the derivative equals to 0. So now in this case, we have a rational expression being set to 0. On the one hand, we need to find the values where either the numerator, I know this is weird, 1 equals to 0, there's nothing that we can do about it, or where x squared equals to 0. That is, again, x equals to 0 will be our critical value. So let's do the same that we did before. Let's do our number line, and the test values will be again negative 1 and 1, negative infinity to 0. Those are the intervals that we break this number line into when we plot these critical values. And well, we're going to choose that test values and find the sign of the derivative. So we will look at the sign of these derivatives. That is, okay, so we are going to test x equals negative 1 and x equals to 1. For the f prime evaluated at negative 1, we are going to do, again, we test this at the derivative. And the derivative is this one where I'm highlighting this function. So that's negative 1 over quantity squared. And that's plugging in the number, negative 1, negative 1. So first of all, negative 1 squared is positive 1. 1 over 1 is 1 times the negative in the front. That's going to be negative 1. This means that we are going to have a negative derivative. On the other hand, if we test 1, and 1, so that's 1 squared, which is 1, and then 1 over the 1 that we obtained before is still 1 times the negative in the front will be negative 1, which is also a negative number. Well, again, we maybe need to do this less than 0, negative, also less than 0, negative. And well, what are we going to have here? Decreasing, and also decreasing. That is, the graph is going to go from negative, again from negative. All right, for this reason, no relative extrema. No relative extrema for this one. There is no maximum, there is no minimum. So NA and does not apply, not applicable. And well, of course, here is the graph of f of x equals to 1 over x. As we know, well, there is this asymptote here. Well, it's actually very well marked down. And well, the graph, see how in this case, decreases and also decreases. It decreases all the time. So for this reason, well, even though yes, there is a critical value, well, there is no max and no min. And it also happens to be undefined for that critical value. Let's look at another example, one for which we are going to use other differentiation techniques. In this case, well, we have f of x equals x squared plus 4. And because we have in this case the quotient of two functions, we are going to use the quotient rule rather. So, well, we're going to do exactly the same. Find the critical values and do the derivative first and then set it equal to 0. Okay, number one, let's recall what the derivative with respect x of a quotient is, u over v. Well, you can use a u and v or f of g, but because I already used f over here, I don't want to use f twice. So that's going to be u prime v minus v prime u divided by u squared. All right, u to the second power, where this is our u, and this is our v. The numerator and the denominator are u and v. So let's take the derivative of this function using the quotient rule. So f prime of x is the derivative of the numerator, which is 2x, times the denominator without differentiating, which is just x, minus the derivative of the denominator, which is 1, times the numerator without differentiating, x squared plus 4. And then the whole thing divided by x squared. So this means we will get 2x squared minus x. Be careful here because this negative will affect everything here. So, well, actually, let me do the following instead. I'm going to multiply this parentheses, x plus 4 times 1, which will simply be x squared plus 4 over x squared, and then distributing the sign, we will get the following: 2x squared minus x squared minus 4. And combine like terms in the numerator, we get x squared minus 4 divided by x squared. And I like this particular example because this time we will, when we set up the derivative, when we set the derivative equals to 0, that is x squared minus 4 divided by x squared. Now we will look for the values that make number one, the numerator equal to 0, but also the denominator equals to 0. In other words, we're looking for the values where number one, the derivative is 0 and the derivative is undefined. Well, it's undefined because it's in the denominator. Okay, so that we already did this x squared minus 4. Yes, I know I did a silly mistake. I'm not going to do it anymore. X plus 2 times x minus 2. And well, x equals to 0. Take the square root on both sides. No need, well, I'm going to write down the plus or minus, even though, well, it's going to be 0. So that's x equals to negative 2, and x equals to 2. So we are going to have this time three critical values for which I think I needed an extra additional column on the table. So, but don't worry, I'm going to make it. So 1, 2, and 3 critical numbers. So what are we going to have over here? Let's see. So we will have, okay, let's do our number line. The one in the middle will be our 0, negative 2, and 2. That is, we're going to have, in this case, we are going to have 1, 2, 3, and 4 intervals to test, which means, again, I needed an extra column on this box. I'm just going to do it by hand real quick. No big deal. It's doable. All right. Okay, so let's define these few intervals. And number one will be from negative infinity to negative 2, and then from negative 2 to 0, and then from 0 to 2, and the last one from 2 to infinity. Okay, so and let's pick test the values. So over here, I'm going to go negative 3, negative 1, 1, and 3. Those are the test values that are within each containing interval. So let's write them down here. So negative 3, negative 1, 1, and 3. And we are going to test the sign of f of x. All right, so recall that f prime of x is, let me write it down here. F prime of x equals to x squared minus 4 over x squared. Okay, so let's test. And we are going to test actually 4 values. I know I have room for 3, but don't worry, I'll make room for the 4th also. So let's do one at a time. Negative 3, test negative 3. That is f prime evaluated at negative 3. That's a negative 3 squared minus 4 over negative 3 squared. Negative 3, negative 3, negative 3. This will reduce to negative 3 squared, which is 9. 9 minus 4 over 9, which is 5 over 9. But again, we really don't care about the sign of the function. What we really care over here is the sign of the derivative, not really the value, so which in this case is positive. We're gonna mark this over here as positive. Okay, let's test x equals to 0 on the derivative. F prime evaluated at 0 will be 0. So actually, let me erase the number. So use a different color. 0 squared minus 4 over 0 squared. That's oh come on. 0, 0, 0. Well, that's 0 minus 4. That's negative. Negative 4. Well, you know what? Unfortunately, oh, it's not 0. It's supposed to be 1. Never mind. Negative 1, not 0. 0, it's actually the critical number. So negative 1 squared with 1 minus 4, that's a negative 3 over 1, which is negative 3, which in this case is a negative number, is less than 0, negative. So let's mark this down over here as negative. Okay, the sign of f prime. Let's test. I will test x equals to positive 1 on the derivative, of course. F prime at 1 that equals to 1 squared minus 4 over 1 squared. And let's plug in 1, 1, and 1 equals to 1 squared minus 4, which is negative 3 over 1. That's also negative 3, which happens to be less than 0 or negative. So we still need to further test this value. So test, I'm going to do it over here, test x equals to 3. So that is f prime evaluated at 3, that's 3 squared minus 4 over 3 squared. Plug it in the 3. Let's plug in the 3. And well, it's basically the same result as before. 9 over 4 over 9, which is 5 over 9, which is positive. And let's fill in the table with a positive sign. Conclusion, we will conclude that this is increasing. You can actually abbreviate as inc, decreasing, another decreasing function. Just dec, it's fine. And inc for increasing. Okay, let's go to our number line and see. Okay, it's going up, increasing, decreasing, again decreasing, and a second time increasing. Well, what are we going to have? In this case, we go from up to down. Here we're going to have a rel max. Here we don't have any change from decreasing to increasing or from increasing to decreasing. In fact, we go from decreasing to decreasing, and then from decreasing to increasing, we are going to have a rel min, a relative minimum. So let's find the coordinates of the relative minimum. So over here on the original function, and the original function f of x equals, what was the original function? That's x squared plus 4 over x. So relative maximum at x equals -2. So evaluate the function, not the derivative. That is at -2. These are too tiny. And well, let's simplify. So -2 squared, which is a 4, plus 4, that equals to 8, divided by -2, that equals to -4. So the order pair will be, the relative maximum will be -2, -4. Okay, so that's the rel maximum. And for the relative minimum, evaluate the original function at x equals to 2. For 0, we don't test anything. We don't plug in anything. In fact, recall that that was one of the restricted values. So that's 2 squared, which is 4, plus 4 over 2. That's 8 over 2, which in this case is also, which is 4. And the corresponding order pair is the 0.2, 4. All right. And well, let's see, what about it? Here it is on the graph. In this case, I got the graph from the graphing calculator, not the graph from the textbook format, because well, I kind of got this example from the exercises, so I didn't have that same access for the graph. And well, if we go -1, -2, -4, this is where the rel max is, and this is the 0.2 comma 4, 2 comma 4, that is where the rel min is. And in fact, again, this function has a vertical asymptote over here, a next value for which the function is undefined. Okay, let's go ahead and look at one last example. So this last example is going to be very short actually, but the reason for which I'm doing this example is because of the weird exponents and the algebra that is involved. Again, before going with that example, I would like to go back to the previous example and highlight the intervals where the function is increasing and the intervals where the function is decreasing, which actually check with what we have on the table above. It's increasing negative infinity to 2 and 2 to infinity, and decreasing otherwise between negative 2 and 0 and 0 and 2. So let's see, for the function f of x equals to 4 times 2 over 11x plus 2 raised to the 8 sevenths plus 1. So I got this from one of the exercises in the homework that it's going to be very useful to work with rational exponents as solving the equation. So, but I mean, let's see. All we have to do to take the derivative of this function is to use the chain rule. So 8 over 7 times 4 times 2 over 11 x plus 2 to the 8 sevenths minus 1, and the derivative of 1 is 0. So in this case, well, 8 sevenths minus 1 is going to be, well, it will be 1/7, and then 8 times 4, which is 32 over 7, that's simply 32 over 7. So that's the derivative of the function. And of course, if you want to change this to radical form, that's fine. 32 over 7, 7th root of 2 over 11x plus 2. Alright, so let's set the derivative equal to 0 to find the critical values. And I know this function, this derivative, contains very crazy numbers. Trust me, this is going to simplify very, very nicely. You will see what's going to happen. So 32 over 7 times the 7th root of 2 over 11x plus 2. Set it equal to 0. Okay, so we need to get rid of this radical. However, before doing that, I'm going to get rid of the coefficient in the front of the radical. So let's see. Multiply both sides, 7 over 32. 7 over 32. So we can cancel the 7s and the 32s, leaving us only with the radical, the 7th root of 2 over 11x plus 2 equals to 0 times this fraction. It's still 0. So we need to get rid of this radical by doing the opposite. So for example, when we have a radical, the square root, we get rid of the square root by squaring both sides. If we had, okay, let me write it down. When we have the square root of x equals to 2, we square both sides to cancel the radical. X equals to 4. When we have a cube root of x, we want to cube both sides to cancel the radical. X equals to 8. So in this case, because we have the 7th root, we need to raise both sides to the 7th power. To cancel the index with the power, raise both sides. Well, 0 to the 7th power will still be 0, and 2 over 11x plus 2 equals to 0. Okay, so let's see. Let's solve this baby equation. Ultimately, this is simply a linear equation. Subtract 2 from both sides to cancel these 2's, and we will be left with 2 over 11x equals to negative 2, and multiplying both sides by 11 over 2, that's to cancel these coefficients, and notice how these 2's are also going to get canceled, and our critical value will be x equals to 11 times the negative, which is negative 11. So that's our critical value. Only one critical value. That's nice. That's really nice. Let's write down this the usual number line and mark down our critical number, negative 11. And well, notice we're going to have 2 intervals to test. Okay, no need to label those, but we need to describe this using interval notation. This interval is essentially negative infinity to negative 11, and the second interval is negative 11 to positive infinity. And well, we are going to choose a test value. I'm going to use negative 12, and we can use negative 10. However, 0 would be an easy number over here. Alright, so the test values are negative 12 and 0. And let's find the values of x. So, negative 12 and 0. And let's recall that the derivative, oh yes, is 32 over 7. Let me write it down, f prime, just so I don't scroll back to scroll the page every time. And that's 2 over 11. 2 over 11 times x plus 2. All right. Well, so in this case, what are we going to obtain? Well, actually, you know what? I'm going to do something different in this case. So I'm gonna change my mind with the first test value with this negative 12. I'm gonna use a different number. So I'm gonna use a number that when I plug in on the derivative, I don't get like decimals, and that is I get a number that is easy to compute. You know, what do I mean by this? Well, so when I would like to use a number for when I plug in over here on the x can be divided evenly with 11. Okay, so unfortunately the number negative 12 that I chose initially is not going to work really nicely. So I'm going to use a different number. I'm going to use negative 22 instead. Okay, because 22 it's a multiple of 11, or negative 33, or negative 44, you know, a number that is easy to compute. So in this case, well, we can do, let's see, negative 22. Let's test the negative 22. Let me change it over here as well. So the derivative f evaluated at negative 32 will be 33 over 7 times the 7th root of 2 over 11. So negative 22, and well, so 22 over 11, that's a 2, or negative 2 rather. Negative 2 times 2, that's a negative 4. Well, so we're going to have 32 over 7 times the 7th root of negative 4. However, you may not want to spend time computing this on the graphing calculators, because it turns out that whenever you might want to recall from intermediate algebra that when you evaluate a radical of odd index, you are okay to evaluate radicals of negative numbers as opposed to radicals with even index. You know, like the square root of a negative number, you cannot do that. Well, you can, but you're gonna get an imaginary number. The 4 root of a negative number, you cannot evaluate it. Well, you can technically, but you get an imaginary number. And so for the 6th root, the 8th root, 10th root, 12th root, etc. All even numbers. However, for cube roots, 5th roots, 7th roots, like the one that we have here, we can do it. And when we evaluate this, it doesn't matter what the value is. Ultimately, this will be basically we can take out this negative, and whatever that value is in decimals, we don't care actually. This is a negative number. This is a negative number. And well, let's do the same for 0. F prime at 0, 32 over 7th root, 2 over 11 times 0 plus 2, 0, 0. What are we going to get? Well, 0 times 2 11s, that's simply 0. And this is the same as 32 over 7 times 7th root of 2. And again, we really don't care about what the value of this is in decimal. Well, if you want, that's fine. Let me highlight this. So that's fine, but ultimately what we're looking here is at a positive number. So that is plus, that means decreasing and increasing. Okay, so in other words, this graph is having the following behavior, going down and then going up. That means in this case, we are going to have a relative minimum. And this relative minimum, we will evaluate it back in the original function. Well, relative maximum, not applicable because we didn't get any maximum over here. But the relative minimum in the original function, f of x, let me go back to the original function for 2 over 11 plus 2, okay? That's a 4 times 2 over 11x plus 2 to the 8th sevenths plus 1 and evaluate f of the critical number, which is negative 11. I know this one looks it's starting to look a little bit crazy, but trust me, a lot will simplify very, very nicely. So this will be plug in, what is that? Oh, negative 11 was the critical number. Okay, so what is going to happen inside of the parentheses? Well, these 11s cancel. That's going to be 2 times a negative 1. That's a negative 2. This will be 4 times negative 2 plus 2 to the 8th over 7. That doesn't matter because negative 2 plus 2 zeroes out. That becomes a 0. And ultimately, we will be left with only this one right here. So the rel min will occur at the point negative 11 comma 1. All right. And yes, I did one that at the beginning looks a little bit crazy. Yes, because of just to show you what to do in a situation like this when you're working on the homework. All right, so yes, this is the end of this section after a number of exercises, so you can see the differences in each situation. How do we treat each case? How do we get a max? How do we get a min? How do we get really nothing? How do we work with function that give us a fraction, you know? So I think this is a good place to quit, and I'll see you in the next video.